let's be very basic about what MPI is here. So it's a message passing library interface standard. So it's a MPI itself is a specification. It's not a particular piece of software. It's a library. You call it from other languages. The standard specifies the bindings for C and Fortran. Bindings for other languages like Python and so forth are not part of the standard, but you can find such things. And it implements the classical message passing programming model that we were just talking about with some augmentations to improve performance. First defined in 1994, I can't believe it was that long ago. A group of people got together, parallel computer vendors, some computer scientists, and some application people, decided that it was time to standardize a message passing interface. So the process took about 2 years. We met every 6 weeks in a completely wretched hotel in North Dallas. I came to see this as one of MPI's strengths. It started off, people wanted to be involved in this standard. They wanted to watch and see what happened and so forth. But the venue was so horrible that people who were just observers wandered out after a while. And so it was a pretty hardcore group that worked on defining the standard. And it was work, but it was a lot of fun. So implementations appeared fairly quickly. MPI-CH, in fact, started appearing before the standard was finished. Bill and I tried to adapt to the standard every 6 weeks as it changed. You know, you're supposed to wait till the specification is finished before you start programming. No, we did the opposite. But it had the effect that when the standard was finished, the first implementation was available for people to work with. And that implementation was architected in such a way that it was relatively easy for vendors to plug in their vendor-specific stuff for their low-level communication library and keep most of the code portable. So vendors supported it, and now it's completely, we had no idea, of course, when we finished, we weren't an official standard of any kind, whether anyone would pay attention to it. But it seems to have caught on, and now you find it on all parallel machines. And there are free and portable implementations like MPI-CH and OpenMPI. So the timeline went like this. 1994 was when it was first presented. 3 years later, so that was the basic message passing and collective operations. MPI 2 added parallel I/O, or the remote memory access operations, which really didn't catch on so fast. Dynamic process creation, support for threads and C++ bindings. And then, I think this was a good thing, the MPI forum went out of business and things stayed the same for 10 years. And that was the time when people could count on writing an MPI program and MPI wouldn't change the next year or the next 2 years and so forth. However, after 10 years, it was time to capitalize on the things that had been learned by all the experience over the last 10 years. There were a few weak spots, a few things that we got wrong, of course. So in the next couple of years, we clarified things and fixed bugs in the spec and made some small updates. Then in 2012 came MPI 3, which added some major new functions that we'll be talking about tomorrow. And then in 2015, there have been some small updates again to fix some gaps. So let's define some terms. When I say process, I mean an address space, a program, and one or more threads of control. Each thread of control has its own subroutine call stack and its own program counter. So the threads share the address space, and that has some advantages and disadvantages. That is, all threads can access all the memory. And so an old-fashioned Unix process you could think of as a single-threaded process. And in MPI 1, the parallel program that we were writing using MPI functions was thought of in the model as a fixed-size collection of old-fashioned Unix processes, each identified by its MPI rank. It's worth noting that MPI, from the beginning, was never single program, multiple data. It was always possible for different ranks to be executing different programs. And in MPI 2, we define semantics that enable MPI processes to be multi-threaded. So you need some functions and some specifications and some clarity on what the standard is going to say about what an MPI program does in the presence of multiple threads. So MPI communication, so we can think of sequential programming is when there is one single threaded process. That's what the first program you ever wrote was, probably. Parallel programming can have multiple types. One process with multiple threads, like in OpenMP. Multiple single-threaded processes, like in MPI 1, or multiple threaded processes, like in MPI 2. And that's especially going to be covered in this section on hybrid programming. Some people have said shared memory programming is easier because everybody has access to the memory. You don't have to do all this complicated sending and receiving of things. I think that's not true. Those who have debugged large shared memory processes, programs know what I'm talking about. But process or threads do need to communicate. Otherwise, you just have a collection of sequential programs rather than a parallel program. So what MPI is for is specifying the communication among processes with separate address spaces. It says how you get data from one address space to another. Those processes might be multi-threaded. So I think of it this way. The difference between shared memory and an MPI program is that where in shared memory, a thread has access to, the multiple threads have access to the same memory. In an MPI, this is just an old-fashioned MPI 1 program here, let's say the address space is the yellow part. So when a process posts an MPI receive, it's saying, for this little piece of my memory, I'm letting other people write on it. Whereas for shared memory with threads, anybody can write on any of the memory all the time. MPI, in my mind, an easier way to control what's happening is that the process says this little bit of memory, just during the MPI receive, is where I let someone write on this memory, and they can't write on any other parts of my memory. And the send specifies which part of the memory is going to be used to write on that. And of course, we have non-blocking operations, we'll talk more about those in a second, where instead of a receive, where you allow someone to write on your memory between the time MPI receive is called and the time it returns. If you do an MPI receive, an MPI I receive, you're leaving it open until the wait. So any of the time between the I receive and the wait, memory, someone else can write on that memory. So an MPI I receive exposes part of its address space to the, quote, system. And by the system, I mean the operating system plus the implementation code and some non-portable parts of the communication software and so forth. The system can do stuff with that memory. It might use internal buffers, maybe smaller than the application's buffers. But when you do the I receive, you are turning over control of your memory to the system. The I send tells the system where the data to be moved is and which process is supposed to have a receive buffer for it. And at that point, where you have an I send and I receive, both of these buffers belong to the system, and it can move data from one to the other, maybe all at once, maybe it can only move small bits of data at a time, so it makes many moves. And when you do the wait on either side, that delays the caller until the system is done with it. So on the receive side, it means all the data is there, and then you can start using it. And on the send, it means that the data has been sent, and so you could rewrite stuff into that buffer. So the blocking operations can be dangerous, and in fact, at one point, we were not going to have them in MPI because they were dangerous. There would be only non-blocking operations. But people had already started to use message passing systems, and they were used to systems that had blocking sends and receives. So that there was only one function called to send or receive a message. So they're there, but one should be careful about them. So there are two kinds of danger. One is the deadlock danger. And what we're talking about here is a situation in which the message is large, so the system might not have room for it all at one time. It might have room only for part of it at a time. So suppose you have an exchange. Processes 1 and 2 are just going to exchange data. So process 0 is going to send to 1, process 1 sends to 0, and then they receive those messages. So this might work, but it might not. If you think about it, the send, suppose the message cannot be absorbed by the system because it's too big. Well, now there is a place for that to go because the system could put it in the receiver's buffer bit by bit, but the receive hasn't been posted yet because process 1 is doing the same sort of send to a long message back to process 0. And so there can be a deadlock. That's one bad thing. And there's also a performance danger. Suppose that you do a send, again, the send can't complete until it can get some of that data into the receiver's buffer. But if he doesn't receive for quite a long time, the send will block, and you may not really want it to do that. So both problems are solved by the non-blocking communication. If you wanted to exchange messages, you post both receives first. That tells the system where the buffer is on the other side for the data to go, in case it has to move it bit by bit. And then you do the sends, and then you do the wait. So that lets you do the same thing. That is, lets you exchange messages, but without the deadlock. And similarly, if you post the receive early, then the send can complete and doesn't have to wait. And the buffered send on the sending side, MPI Send is the buffered send in which you supply a buffer for the system to use on a big message. So let's talk for a little bit about overlapping communication and computation. A common misconception about the non-blocking operations is that the reason they're there is to allow communication or computation to take place at the same time as the computation. Did I say computation and computation? I meant the two things, communication, computation taking place at the same time. That's not the real reason. The reason they exist is for the reasons that we just talked about, to avoid deadlock and delays. It's true that it allows an implementation to do that if the system supports it, but it's not part of the specification. And if in your environment you find that you're not getting overlap, it's not the fault of the MPI standard. It didn't specify that that had to happen. So especially specialized communication software can sometimes do that. But the real purpose is what we've just been talking about. Actually, there are quite a few different things that an implementation can do and still conform to the standard. So it can use a system thread or hardware support in order to move data in parallel with local computation. That's what you would like, but your system might not have that separate thread or that special hardware. Remember, a very important part of the MPI spec was to be portable to a wide range of machines. It might move all or part of the message during some other MPI call. So between the I send and the wait, you might call something else, like MPI test. The MPI implementation says, since you've just called it, says, oh, I've got an ongoing send here. I can kick the next bit along. Or if the system can absorb the whole message, then it can treat the I send as if it was a normal blocking send and just complete the I send right away. Or it can actually wait until the very end, and so that all the communication takes place during the wait call. So it's particularly important to understand this if you're timing the MPI calls, because the MPI spec doesn't tell you exactly what's going on in each of those calls. So let's summarize the various kinds of send. MPI Send Blocks, that's probably the first MPI function you learn to use until the message is absorbed by the system. So it may have been received, it may be in transit, whatever, but it blocks until the buffer, your copy of the buffer is no longer needed. iSend doesn't block, so it should always return quickly because it's the iSend, all it has done is tell the system where the data is that has to be sent. It's just giving the system an address. What the system does with it is up to it. send, the synchronous send, blocks until there's a matching receive. So this is useful because when the matching receive is posted, now there's a place to put the data. And so it can go, but it blocks until that other receive is going. And then there is the ready send. The ready send assumes that that corresponding receive has been posted. So it's your job to make sure that it has. Something very bad will happen if you haven't. So how can you be sure that it has been posted, and what good is this anyway? So one common situation occurs when one process is asking another process for some information. So one way to use the rsend is this. So this is the asking guy. So he posts an I receive for the answer. So now the buffer is here for the answer to arrive. And then he sends the question. So since you wrote both sides of this, you know that he's not going to send the answer before he gets the question. So you do this receive, and now just because the receive is completed, you can be sure that the I receive was posted, so you can use an rsend. And that can, especially for large messages, speed up the response of the system. A few words about collective operations. So there are many collective operations. You've used some of them, I'm sure. And in some cases, computation is included. Implementations use lots of different algorithms for this. And MPI-CH uses several depending on the situation, based on the message sizes, the machine topologies, capabilities of the system, and scalable algorithms in this very large space of possible ways to do it and the machines to do it on remains a research topic. Common feature that what makes it a collective operation is that all the processes must call this in a communicator. Something worth noting for people who measure performance is that measuring the performance of collective operations has a pitfall in it. So if you're measuring the time of a collective operation, sometimes that can obscure what's really not slowness on the part of the collective operation, but a load balancing problem in the computation. So suppose you do a computation on 3 nodes, and then you do an all reduce. Well, suppose there's the amount of computation done on each process is widely different. So each of them computes and then calls all reduce. So you measure the time of the all reduces, and you say, oh, all reduce is really slow. But the real problem is that the all reduces didn't start at the same time. They were delayed by the large amount of computation in this node. So this is just something to be aware of when you're measuring the performance of collective operations. You have to think about exactly what's happening when they start and when they finish. So a few words on MPI 2. That introduced dynamic process management, remote memory access, the one-sided operations, parallel I/O, and thread safety. Also C++ bindings, they didn't really stick. And in MPI 3, the MPI forum took them out. And there are also Fortran bindings. So we're not going to talk this week about dynamic process management. It's not universally implemented. It's quite a bit different from the other MPI stuff because it interacts with the operating system in a deeper way, so it's hard to be portable in the implementation. And it may involve the batch scheduler of the system. That is, creation of new processes is something that many schedulers are not really ready to deal with. So we're not going to talk so much about that. We're going to talk about thread safety under hybrid programming. 1 or 2 things about remote memory access. So what happens in MPI's RMA, remote memory access, there are things called window objects. So a window is like a window object is like a communication buffer, but it's used a slightly different way. So when a process allocates a window object, that's a piece of memory that other processes can write in maybe for quite some time, and it also might be large. There's room for multiple communication buffers. The MPI window, that's a collective thing, that's the collection of all the window objects. So what it does is, remember we were talking about in MPI 1, the communication buffers are the part of the memory that's being made accessible to other processes. So an MPI window object is a bigger area that lasts for a longer time, not just the extent of one call, but until you're done with it. So you can create a window. There are 3 operations. You can put things in another process's window, not his whole address space. He only exposes his window, just like exposing a receive buffer. You can get things from another process, and the MPI accumulate lets you do some computation at the same time that you're retrieving data. And then the synchronization is completely separate, and we'll talk about that when we talk about these tomorrow. Another part of MPI 2 is parallel I/O. Parallel I/O was going along separately from MPI for a while. There was a group trying to define a parallel I/O standard. And the 2 groups got together based on this kind of an analogy. So if you read from files or write to files, it's a little bit like sending and receiving a message to the file system. And we can use some concepts from MPI. And in fact, if we wanted a really robust parallel I/O system, we would need something like them if they weren't exactly the same. So MPI data types are great for describing non-contiguous data, both in memory and in files. That is, for scattering things across a file system or reading them into non-contiguous data in memory. You also need non-blocking operations, or those are common in I/O operations, and also collective operations, because collective reads and writes can really make a huge difference in performance. So it was realized that since you needed a lot of MPI type stuff, we might as well just absorb parallel I/O into the MPI standard, and that was done in MPI 2. One specific MPI implementation that we're familiar with because we wrote it. It's a widely portable implementation of MPI. It's not the only one, but we're quite familiar with it, and it provides all the features of MPI, including the MPI 3 stuff. It serves as the foundation for most vendor implementations. So for example, if you run on Vesta or Mira, you're using an MPI-CH-based MPI implementation. It's still being developed at Argonne and at UIUC. And we also have several other collaborators who contribute features and bug fixes and so forth. The current release is MPI-CH 3.2, which you can put on your machine tonight. And you can run experiments here on either your Mac OS laptop or your Linux laptop. So I have a set of instructions on exactly what to do. So I'll just sort of show you the level of detail that's here. So just exactly what you can, some step-by-step, so that at the end of the day you will have run some MPI programs on your laptop. There are tutorial books. Can't help plugging these books. I think they're pretty good tutorial type stuff as opposed to the standard. The standard is available on the web. It's the final word, but there's more explanation of why things are the way they are and more examples and so forth in these books. There's some example codes here. Okay, thank you very much.